The Great Tapestry of Life, from Primordial Soup to Dinosaur Kings. One breath. That is all it takes for us to inhale the very air that sustains us, the air that flows through our lungs, rich with oxygen. But what if I told you that for billions of years, our planet was a suffocating world, utterly devoid of this life-giving gas? A world where the very elements of existence were locked in a cosmic dance of fire and fury, waiting for a whisper of life to begin the grandest story ever told. This isn't just a tale of ancient Earth, it's the epic saga of how life itself ignited, evolved, and reshaped a barren rock into the vibrant, breathing world we know today. It's a story of deep time, unimaginable transformations, and creatures so colossal they defy belief. Imagine a planet, freshly formed from cosmic dust and gas, a searing inferno of molten rock, constantly bombarded by colossal asteroids. Rivers of lava flowed across its surface, and the sky, if one could even call it that, was a toxic shroud of methane, ammonia, and carbon dioxide. There was no blue, no green, no hint of the vibrant ecosystems that would one day flourish. This was Earth, approximately 4.5 billion years ago, a nascent world in its Hadean Eon, a period so hostile it was named after the Greek god of the underworld. The very notion of life, fragile and intricate, seemed an impossibility. Yet against all odds within this crucible of chaos, the first sparks of life would ignite. From primordial whispers, a biochemical miracle would unfold, giving rise to the simplest single-celled organisms, the ancestors of every living thing that has ever graced this planet. They would be the silent architects of change, slowly but inexorably transforming the very air and oceans, paving the way for an explosion of multicellular forms, the colonization of land, and eventually the colossal reign of the dinosaurs. This journey, spanning billions of years, is a testament to the astonishing resilience and adaptive power of life, a narrative filled with staggering leaps, cataclysmic extinctions, and breathtaking triumphs. In this video, we embark on an unparalleled voyage through Earth's deep past. We will witness the birth of our planet, the mysterious genesis of life in its harshest conditions, and the monumental shifts that turned a fiery rock into a blue marble teeming with biological wonders. We will trace the evolutionary path from the most basic cells to the astonishing diversification of the Cambrian explosion, the audacious conquest of land, and the dramatic rise and fall of the dinosaurs, the undisputed rulers of the Mesozoic era. Prepare to have your understanding of time, evolution, and existence profoundly expanded as we unveil the true dawn of Earth's life. This is not just a history lesson, it is an epic story, painted across eons, starring geological forces, atmospheric transformations, and the countless, often invisible, ancestors who shaped our world. It is the story of how our planet came alive, and how, against all odds, life not only survived but thrived, adapting to unimaginable changes and repeatedly reinventing itself in the face of cataclysm. From the tiniest microbe to the mightiest dinosaur, every creature plays a vital role in this grand narrative, a testament to the incredible journey of life on Earth. Historical context and setup our story truly begins in the Hadean Eon, from about 4.6 to 4.0 billion years ago. The name, Hadean itself, derived from Hades, the Greek god of the underworld, perfectly encapsulates the brutal conditions of this era. This was Earth's fiery infancy, a period when our planet was not merely hot, but molten, a searing ball of liquid rock. Intense volcanic activity spewed gases into an early atmosphere that lacked free oxygen, a stark contrast to the breathable air we enjoy today. During this tumultuous time, Earth was also subjected to what scientists call the late heavy bombardment, a relentless onslaught of asteroids and comets. These extraterrestrial impacts were so frequent and powerful that they would have repeatedly vaporized any nascent oceans, ensuring that the planet remained a hellish, uninhabitable landscape for millions of years. This relentless cosmic pummeling was a shaping force, not just for Earth's surface, but also for its very composition. Around 4.5 billion years ago, a colossal event occurred that would forever change Earth's destiny. A Mars-sized body, sometimes called Theia, is thought to have collided with our planet. This gargantuan impact not only reshaped Earth, but also led to the formation of our moon, a celestial companion whose gravitational pull would stabilize Earth's axial tilt, creating the relatively consistent seasons vital for life's long-term evolution. Without the moon, our world might have been a chaotic tumble of extreme climate shifts. As the Hadean gave way to the Archaean Eon, from about 4.0 to 2.5 billion years ago, Earth began to slowly, painstakingly cool. The molten surface solidified into the first stable crust, and as temperatures dropped, water vapor in the atmosphere condensed, unleashing torrential rains that lasted for millions of years. These endless downpours filled the planet's depressions, giving birth to the first oceans, vast bodies of water that would become the cradle of life. The early atmosphere was still inhospitable, dominated by gases like methane, ammonia, and carbon dioxide, but the presence of liquid water was a crucial prerequisite for what was to come. It was within these primordial oceans, shielded from the sun's harsh UV radiation, that the first stirrings of life are believed to have occurred around 3.8 to 3.5 billion years ago. Scientists hypothesize that deep-sea hydrothermal vents, spewing superheated, mineral-rich water from Earth's crust, could have provided the chemical energy and raw materials for life's genesis. Alternatively, shallow, sun-drenched pools might have offered another potential birthplace. Regardless of the exact location, these were the perfect chemical laboratories for organic molecules to spontaneously form, self-assemble, and eventually self-replicate. These earliest life forms were simple, single-celled organisms known as prokaryotes, bacteria, and archaea. They were anaerobic, meaning they thrived in the absence of oxygen, which was still virtually non-existent in the atmosphere. For over 1 billion years, these microscopic pioneers would be the sole inhabitants of Earth, slowly evolving, adapting, and subtly changing their environment. Their existence was a testament to life's profound ability to emerge from non-living matter, a process known as abiogenesis, which remains one of science's most profound mysteries. Then came the game changer, the evolution of Cyanobacteria, around 3.5 billion years ago. These revolutionary microbes developed the ability to photosynthesize, harnessing the sun's energy to convert carbon dioxide and water into food, with oxygen as a waste product. Initially, this oxygen reacted with iron in the oceans, forming vast deposits of banded iron formations that still tell this story today. But over time, the oceans became saturated, and oxygen began to seep into the atmosphere, leading to the Great Oxidation Event around 2.5 billion years ago. This was a global catastrophe for many anaerobic life forms, to whom oxygen was a deadly poison. Yet, it was also the ultimate evolutionary catalyst, paving the way for aerobic respiration, a much more efficient way to produce energy. It also led to the formation of the ozone layer, a protective shield against harmful UV radiation, which would eventually allow life to emerge from the oceans and colonize land. This shift was profound, transforming Earth from a hostile, oxygen-free world into one capable of supporting complex, multicellular life. The Proterozoic Eon, from 2.5 billion to 541 million years ago, was a time of immense, yet often hidden, change. Not only did the atmosphere oxygenate, but another crucial evolutionary leap occurred: the emergence of eukaryotic cells, around 2 billion years ago. These cells were far more complex than prokaryotes, featuring a nucleus that housed their genetic material and specialized organelles like mitochondria, which are essentially ancient bacteria that became integrated into the larger cell through a process called endosymbiosis. This increase in cellular complexity was the foundation for everything that followed. Towards the later stages of the Proterozoic, around 1 billion to 540 million years ago, multicellular organisms began to appear. These early complex life forms, known as the Ediacaran biota, were often soft-bodied, enigmatic creatures, some resembling quilted mats or frond-like structures. They represent a crucial stepping stone from single-celled life to the explosive diversity of animals we see today. Earth's climate during this era also fluctuated wildly, including several snowball Earth events, where the planet was almost entirely covered in ice, posing immense challenges for the burgeoning life forms. The story unfolds our journey now brings us to one of the most astonishing chapters in the history of life: the Cambrian explosion. Approximately 541 million years ago, after billions of years of slow, incremental evolution, life on Earth suddenly, spectacularly, diversified. Within a geologically brief period of tens of millions of years, an unprecedented array of animal body plans emerged, filling the oceans with a bewildering diversity of forms. It was as if life, having painstakingly built its foundational blueprints, suddenly discovered a boundless capacity for innovation. This period saw the appearance of most major animal phyla that exist today, creatures with hard exoskeletons, complex sensory organs, and the beginnings of predatory and defensive behaviors. The fossil record from sites like the Burgess Shale in Canada offers a stunning snapshot of this ancient ocean, revealing creatures like the fierce Anomalocaris, a top predator with segmented eyes and formidable grasping appendages, or the armored Wiwaxia and the famously spiky Hallucigenia. This rapid diversification was likely driven by a combination of factors: rising oxygen levels enabling more energetic lifestyles, the evolution of key genetic toolkits like Hox genes that govern body plan development, and an escalating arms race between predators and prey. Following the Cambrian, the Paleozoic era unfolded, a long epoch spanning from 541 to 252 million years ago, witnessing the continued flourishing of marine life and the audacious colonization of land. In the Ordovician period, around 485 million years ago, primitive plants began their slow, arduous journey onto barren land, transforming rocky shores into nascent green fringes. They were soon followed by fungi and early terrestrial arthropods, like millipedes, which were among the first animals to breathe air and walk on solid ground. A pivotal moment for our own lineage occurred around 400 million years ago with the evolution of the first vertebrates. Fish. These early aquatic creatures developed internal skeletons, a revolutionary adaptation that provided structural support and enabled greater mobility. The Silurian period, from 443 to 419 million years ago, saw the diversification of jawed fish, a game changer that allowed for more efficient predation. Pichea, a primitive chordate from the Cambrian, with its rudimentary notochord, hints at the very deep roots of our spinal column. The Devonian period, often called the Age of Fishes, witnessed an explosion of fish diversity. Critically, during this time, a group of fish known as lobe-finned fish evolved. Unlike their ray-finned relatives, lobe-finned fish possessed fleshy, muscular fins containing bones, precursors to the limbs of terrestrial vertebrates. Around 375 million years ago, transitional forms like Tiktaalik, with its fish-like scales and fins but a flattened skull and weight-bearing ribs, provided a stunning bridge between aquatic and terrestrial life. It could walk on its fins in shallow water, venturing onto land for brief periods. This brave step out of the water led to the emergence of amphibians, the first vertebrates to truly colonize land, around 360 million years ago. While they developed lungs for breathing air, they remained tethered to water for reproduction, laying their eggs in moist environments. The Carboniferous period, from 359 to 299 million years ago, saw vast swamp forests cover much of the continents, creating the immense coal deposits we mine today. High atmospheric oxygen levels supported giant insects, and amphibians flourished, becoming the dominant terrestrial vertebrates. But the land was not yet fully conquered. A major evolutionary innovation arrived with the first reptiles, which evolved in the late Carboniferous. The key to their widespread success was the amniotic egg, a self-contained private pond that allowed them to reproduce entirely on land, free from the need for water. This breakthrough enabled reptiles to venture far inland, away from marshes and rivers, opening up vast new ecological niches. The Permian period, from 299 to 252 million years ago, saw reptiles diversify extensively, including the synapsids, a group that would eventually lead to mammals, and the sauropsids, the lineage that includes modern reptiles, birds, and dinosaurs. Then came the greatest catastrophe Earth has ever witnessed. The Permian-Triassic extinction, often called the Great Dying, around 252 million years ago. In a geological blink of an eye, an estimated 96% of all marine species and 70% of terrestrial vertebrate species were wiped out. This cataclysm was likely triggered by massive volcanic eruptions in what is now Siberia, unleashing vast amounts of greenhouse gases that caused extreme global warming, ocean acidification, and widespread anoxia, lack of oxygen, in the oceans. It was an event so devastating it almost sterilized the planet, fundamentally resetting the course of life on Earth. From the ashes of the Permian extinction emerged a new era, the Mesozoic era, lasting from 252 to 66 million years ago, famously known as the Age of Reptiles. This period is synonymous with the rise and undisputed reign of the dinosaurs. The Triassic period, the first phase of the Mesozoic, saw life slowly recover. From the surviving reptilian lineages, the first dinosaurs appeared, initially small bipedal creatures. Alongside them, the first mammals also evolved, though they remained small and inconspicuous, living in the shadows of their reptilian cousins. The Jurassic period, from 201 to 145 million years ago, was the true dawn of the giants. Dinosaurs exploded in diversity and size, becoming the dominant terrestrial vertebrates. Colossal long-necked sauropods like Brachiosaurus and Diplodocus munched on vast fern forests, while formidable theropods like Allosaurus prowled as apex predators. In the oceans, marine reptiles such as ichthyosaurs and plesiosaurs ruled, while pterosaurs, the first flying vertebrates, soared through the skies. It was also during this period that the first birds, like Archaeopteryx, evolved from feathered theropod dinosaurs, taking to the air. The supercontinent Pangaea, which had formed in the late Paleozoic, began its slow, inexorable breakup during the Mesozoic. This continental drift reshaped the planet's geography, creating new oceans, influencing global climates and isolating populations, which in turn drove further evolutionary diversification. The Jurassic oceans began to open up, leading to new currents and ecosystems. The Cretaceous period, from 145 to 66 million years ago, saw dinosaurs reach their peak diversity and iconic status. Tyrannosaurus rex, Triceratops, and Velociraptor became synonymous with the raw power and majesty of these ancient rulers. But another silent revolution was also unfolding: the evolution and diversification of flowering plants, or angiosperms. These plants, with their attractive flowers and efficient seed dispersal, rapidly transformed terrestrial ecosystems, providing new food sources and habitats that would shape the evolution of insects and herbivorous dinosaurs. However, even the mightiest reign must come to an end. Approximately 66 million years ago, the Mesozoic era concluded with the infamous Cretaceous-Paleogene, or KPG, extinction event. This catastrophic event brought an abrupt end to the age of dinosaurs, wiping out approximately 75% of Earth's species, including all non-avian dinosaurs. The leading scientific hypothesis points to a massive asteroid impact, roughly 10 to 15 kilometers wide, striking the Yucatan Peninsula in Mexico, creating the Chicxulub crater. The impact unleashed unimaginable devastation: tsunamis hundreds of meters high, global wildfires, and a thick cloud of dust and soot that blocked out the sun, plunging the planet into a prolonged impact winter. Photosynthesis ceased, collapsing food chains from the bottom up. While the asteroid impact is the primary culprit, massive volcanic eruptions in India, known as the Deccan Traps, which had been active for millions of years, likely exacerbated the environmental crisis, adding further stress to an already collapsing biosphere. The end of the dinosaurs marked a pivotal turning point in Earth's history, clearing the ecological stage for a new group of animals that had largely remained in the background for millions of years: the mammals. Having survived the cataclysm, they would now seize the opportunity to diversify, adapt, and eventually dominate terrestrial ecosystems, ushering in the Cenozoic era, the age of mammals, and setting the stage for the eventual evolution of primates and, ultimately, humans. Impact and legacy: the profound impacts of Earth's early history and the saga of life's evolution are woven into the very fabric of our planet and our existence. The most immediate and transformative outcome was the atmospheric revolution caused by photosynthetic organisms. The gradual increase in atmospheric oxygen, initiated by Cyanobacteria billions of years ago, permanently altered Earth's chemistry. This shift not only enabled the evolution of more efficient aerobic respiration, which powers complex multicellular life, but also led to the formation of the ozone layer. This protective shield absorbed harmful ultraviolet radiation, making it possible for life to finally colonize land without being scorched. The emergence of multicellularity and the subsequent Cambrian explosion fundamentally established the blueprint for biodiversity. This rapid diversification, witnessed in the oceans over 500 million years ago, gave rise to a vast array of animal body plans, many of which are still recognizable in the phyla we see today. Without this critical burst of innovation, the complex ecological webs and specialized organisms that characterize modern ecosystems simply would not exist. Every time you see a crab, a fish, or a worm, you are looking at a distant descendant of the Cambrian fauna. The colonization of land, initiated by primitive plants and then by animals, was another monumental achievement. This audacious leap transformed barren continents into lush, verdant landscapes, creating entirely new biomass and food webs. The evolution of the amniotic egg, in particular freed reproduction from water, allowing reptiles to become truly terrestrial. This ecological expansion dramatically increased the planet's overall biomass and biodiversity, altering the very surface of Earth through soil formation and atmospheric regulation. Mass extinction events, though devastating, were paradoxically powerful drivers of evolution. The Permian-Triassic extinction, the Great Dying, cleared the slate for new groups to emerge, most notably paving the way for the rise of the dinosaurs and their reptilian cousins. Similarly, the KPG extinction, which ended the reign of the non-avian dinosaurs, created an immense ecological vacuum. This vacuum was swiftly filled by the surviving mammals, which underwent a spectacular adaptive radiation, diversifying rapidly into a myriad of forms, and eventually becoming the dominant terrestrial vertebrates. Imagine an alternative history. What if the asteroid had missed Earth 66 million years ago? What if the Permian extinction had been less severe or never happened? Our world would likely be a very different place. Perhaps dinosaurs would still roam the Earth, having evolved even more diverse and intelligent forms. Mammals might still be small, nocturnal creatures, confined to the shadows. This comparative perspective highlights the profound role of contingent, often catastrophic, events in shaping life's trajectory. These moments of destruction are also moments of creative opportunity. Today, the legacy of these ancient times is everywhere. The very air we breathe, rich in oxygen, is a direct result of billions of years of microbial photosynthesis. The vast coal deposits that fueled the Industrial Revolution are the compressed remains of carboniferous forests. The oil and natural gas that power our modern world are the fossilized remnants of ancient marine life. Our understanding of Earth's deep history, gleaned from fossils and geological strata, forms the bedrock of modern biology, evolutionary theory, and even our search for extraterrestrial life. Moreover, the study of past mass extinctions provides crucial context for understanding the current biodiversity crisis and anthropogenic climate change. By examining the causes and consequences of events like the Permian and KPG extinctions, scientists can better predict the potential impacts of rapid environmental shifts on modern ecosystems. The resilience, or fragility, of life under extreme pressure is a lesson from deep time that resonates with urgent relevance today, reminding us that even the most dominant species can vanish. The Earth's crust itself bears witness to this epic journey. The majestic mountain ranges, the vast ocean basins, the distribution of continents all are products of plate tectonics, a process that has influenced climate, ocean currents, and the isolation and diversification of species throughout billions of years. Life and Earth's geology have co-evolved, each profoundly shaping the other in an intricate, continuous dance. Reflections and Lessons, the grand narrative of Earth's early life, offers profound insights into the nature of existence itself. What can we truly learn from billions of years of cosmic and biological drama? First, consider the sheer scale of time involved. We often think in terms of decades or centuries, but life's journey unfolded over eons, stretching across millions and billions of years. How does understanding this deep time change your perspective on humanity's place in the universe? Does it make our existence feel more fragile or more miraculous? Second, reflect on the incredible resilience of life. From the hostile crucible of early Earth to the devastating impacts of mass extinctions, life has repeatedly found a way to not only survive but to thrive and diversify. What does this tell us about the fundamental drive for existence and the adaptive capacity embedded within living systems? Third, ponder the transformative power of the seemingly insignificant. The single-celled Cyanobacteria, invisible to the naked eye, fundamentally altered an entire planetary atmosphere, creating the very oxygen that allows complex life to flourish. What other small changes in our world today might be setting the stage for unforeseen future transformations? Fourth, contemplate the role of catastrophe. Mass extinctions were not merely destructive events, they were paradoxically creative forces, clearing ecological niches and driving the evolution of entirely new dominant groups. Does this suggest that periods of profound crisis can also be periods of radical innovation and rebirth, both in nature and in human society? Fifth, think about the intricate interconnectedness of Earth's systems. The atmosphere, oceans, geology, and biology are not separate entities. They are a single, co-evolving system. How does this deep historical understanding inform our modern efforts to address global challenges like climate change, where human actions are profoundly impacting these interconnected systems? Sixth, consider the journey from simple to complex. Life began as primitive cells, gradually evolving into eukaryotes, then multicellular organisms, and eventually the vast diversity of plants and animals. What were the critical steps in this increase of complexity, and what does it tell us about the fundamental principles of evolution? Seventh, reflect on the legacy of the dinosaurs. For over 160 million years, they were the undisputed rulers of the land. Their abrupt end opened the door for mammals to rise, including our own ancestors. Does this remind us of the transient nature of even the most dominant forms and the ever-changing landscape of planetary power? Finally, what does the entire saga of life, from its primordial whispers to the reign of Dinosaur Kings, tell us about our own species? We are but a recent blip on this vast timeline, yet we possess the power to alter the planet on a geological scale. How should this profound history inform our responsibilities as stewards of this incredible living Earth? Outro our journey through Earth's deep history, from its fiery birth to the age of dinosaurs, reveals a story of unparalleled drama, resilience, and transformation. We have witnessed life emerge from non-living matter, reshape an entire planet's atmosphere, explode into breathtaking diversity during the Cambrian period, conquer land, and ultimately culminate in the colossal reign of the dinosaurs. Their sudden and dramatic exit paved the way for the age of mammals, a story that would eventually lead to our own existence. This epic tapestry of life is a testament to the dynamic interplay between geological forces, climatic shifts, and the relentless, adaptive power of evolution. Every rock, every fossil, every breath of oxygen carries echoes of these ancient events, reminding us of the planet's tumultuous past and its incredible capacity for reinvention. The story of life is not a linear progression, but a complex, branching tree, pruned by catastrophe and invigorated by innovation. If you found this journey through deep time as fascinating as we did, there are countless other chapters in Earth's history waiting to be explored. Perhaps you would be interested in learning about the rise of mammals, how a cataclysm forged a new world, detailing the Cenozoic era and the explosive diversification of mammals after the dinosaurs' demise. Or maybe the dawn of humanity, from apes to astronauts, tracing the incredible evolutionary path of our own species. We could also delve into Earth's great freezes, the snowball Earth events, exploring the periods when our planet was almost entirely covered in ice, and how life endured. Or the secret lives of microbes, unseen architects of our world, to understand the ongoing, often invisible, impact of the planet's smallest inhabitants, just as Cyanobacteria once transformed our atmosphere. Each story is a crucial piece of the puzzle, revealing more about the planet we call home and our place within its grand, ongoing narrative. Understanding this deep history is not just about appreciating the past. It is about comprehending the present and envisioning the future. It teaches us about the resilience of life, the fragility of ecosystems, and the profound, often unexpected, consequences of environmental change. It reminds us that we are part of an unimaginably long and complex lineage, connected to every creature that has ever lived, from the simplest prokaryote to the mightiest dinosaur. The story of life is eternal, continually unfolding, and we are its latest chapter. Thank you for joining us on this incredible voyage through time. Please like this video, subscribe for more epic history content, and let us know in the comments which historical journey you would like to embark on next. Until then, keep exploring, keep questioning, and keep marveling at the wonders of our living planet.